Hey, great. Thank you very much. And yeah, thanks for the introduction again. I'm very happy to be talking today about how graph machine learning is reshaping behavioral analytics. I think it's a very exciting combination of two very exciting areas. Of course, for me personally, my research area is graph machine learning, so I'm always excited to be talking about this. Today, it is kind of going to be, as the first slide, as the cover said, a Strawman's intro to graph ML. So we're not going into sort of the mathematical details. It'll be lots of figures, lots of intuition, just so that you have an idea of how things roughly work, and then we can see how this is impacting behavioral analytics. So let's start with sort of a brief recap of what machine learning is, just so that we are all on the same page. Machine learning is all about having a machine learning model. So this is what we can see here in the center. I'm going to be drawing also a bit. So this is the machine learning model here. It's similar to what you expect from any model. You know, we have models in climate science, in all sorts of scientific disciplines. Of course, it's some sort of mathematical representation. It's a lot of maths internally. What we do is we put something in and we expect a certain outcome. Usually we call that like a prediction. In machine learning, this is the case as well. We have some inputs, for example, an image, and we want some output, for example, the classification of that image. So the very common task is image classification. So here we've got the image of a dog, and we want our model to recognize that that's a dog and then tell us that. Of course, it's a very simple task. We sort of move beyond that. We can do much more complicated things, and we'll see that as well. And what's very interesting about machine learning, and that is kind of why it's become so important these days, is that we don't have to kind of develop that model ourselves, but we can sort of outline the model. We can sort of say, well, what should be the rough structure of our model? But then the details, the parameters of our model are learned from the data. So we have sort of a large amount of training data that would be images of, for example, cats and dogs, for which we already have the labels. And then we tune the parameters of our model such that it makes the right predictions. And just to take like a slight look inside, let's open that black box a bit. Internally, we've just got loads of parameters. Here I have them sort of as knobs that you can turn. What we would be doing is, of course, we give this model examples, these training examples, so images of dogs and cats. And initially, it might not make the right predictions, but what we can do is we can use an algorithm that then kind of tunes these parameters to make better predictions. So those might be, maybe after tuning it, we change it to 0.45, 0.1, 0.9. So just making small adjustments to these parameters of the model to get better predictions. So this is the main idea of machine learning. Now, machine learning is a relatively old field, but the most exciting developments in some way have happened over the last couple of years. So there's really a lot going on at the moment, both in sort of the industry side, but also in the research side. And one of the key trends has been kind of incorporating structure into machine learning models. So initially, we've been working a lot with unstructured data, meaning just sort of, lots of numbers. You can think of this more like of an Excel sheet, and you just put these numbers into your machine learning model and you want a certain outcome. They're sort of the core, the most simple machine learning models are based on that kind of data. But if we have some shape, some format for our data, then we can tune or we can adapt our machine learning model to make better use of that kind of data. So examples include sequence data. You can think of some sort of time series, for example, a stock chart, but also text is some sort of a sequence. You know, you always know that one block follows after the other. And that's, it's a very simple structure, but it counts. And there are specific machine learning models that can deal with that kind of data. Image data is, of course, another one. Here we sort of, we know certain properties, right? We know that all of our data will be images, and it has certain features. For example, we know that, well, a dog nose will only appear at a certain point. It won't be like split across the image. So this is something called locality of features. So we just make use of these properties that our data has. And all of this, so the first three are relatively old for machine learning standards. It's such a fast-moving field. There's so many new discoveries and new research papers literally every day. that, yeah, even working on image data is something that we could consider is now not old school, but it has been here for a couple of years now. What's really recent is working or building machine learning models for graph data. So this is what you can see here on the last slide. So this is kind of a new type of input, and we also want to apply machine learning models to that data type. So let's first think a bit about what is actually a graph. Some of you might be familiar with what this is. It's a very common data structure in computer science. On the most fundamental level, a graph is a kind of network. So we have entities. Those are these nodes that here in green, starting here on the left side. Those are the nodes. We also sometimes call them vertices. And then we have connections between these nodes, right? So these are these edges here. We call them edges or connections. And yeah, so a graph models this very fundamental concept of entities connected via relationships. And because it's so general, it's incredibly powerful. We can model almost anything with a graph. You can model social interactions. You know, a social network is essentially that. You can model molecules in chemistry, if you think about that, or you can model biological networks. You can model, yeah, concrete objects, say an airplane. You can represent almost anything with a graph. And that's why it's so powerful when we can make machine learning, when we can apply machine learning to such a data structure. To give a bit more concrete example, let's consider a network of users. You can see here in the middle. So it's essentially, yeah, a number of users that are connected by edges. Those edges, for example, could mean that users, those are employees in a company, that they are communicating, for example, via email. Yeah, and this is how we can sort of nicely represent that in a very abstract but useful way. We can also extend that further. That would be the example here on the right side. We don't need to have only a single type of node. We can incorporate different types. So we can also model documents as nodes here. And then if someone accesses a document, for example here, then you can see, well, we draw an edge between an employee or a user and that document or that piece of data. And I hope that already gives you an idea of how powerful it is to model sort of real world scenarios using a graph. Okay, let's go a bit further. Usually, when we do machine learning, we don't just have sort of that connectivity structure. We don't just know sort of who's connected to whom, but we also have information associated with each entity. Again, if we think of a company structure, we have employees, then we have information about these employees. For example, their role, are they a developer, human resources, public relations, etc. And maybe also the year that they joined the company. So those are the features that you can see here. Now, in normal machine learning, what we would have done in the past is that we would have to consider each of these employees, each of these sort of data entities or data samples on their own. They're just sort of, yeah, independent of each other. There's no connection. We feed those into our model and we get some prediction for that employee. Now, with graph machine learning, crucially, we can incorporate these relationships, right? So we can incorporate the information that there is some sort of connection between this person here and this person and this person. And that, of course, contains valuable information, right? So we know, for example, if the edges represent email communication, and we know that, for example, these two people work closely together because they send a lot of emails, or those here. And we also know sort of that human resources is maybe in touch with more people of the company, so they've got quite a central position in the graph. They work with maybe someone else from human resources and with public relations, with finance and other developers. So here you can kind of already see there's valuable information in that graph structure. And ideally, we want our model to be able to make use of that information. And yeah, so how would we be able to do this in machine learning? How can we incorporate, again, this is sort of the one of these trends that we've talked about before, how can we incorporate structure into a machine learning model? Now, when initially the first sort of generation of neural networks are these so-called fully connected neural networks, you can see this here. We don't have to go into the mathematical details. They're often represented in the way you can You can see here in the middle. They're often represented in this way with these nodes, or like these neurons, and then they're connected to other neurons. Essentially, you just feed in your vector, your data, and you get some output. But your model doesn't really consider any sort of, any of the structural properties of the input. That though looks different if we, for example, want to work with images. A very common architecture for images are the so-called convolutional neural networks. You might have heard of those before. This is a neural network architecture, so a machine learning model adapted to work with images. Now, why does it work with images? Well, kind of if we look a bit into the internals of that architecture, what we see is that the network kind of knows that what it's working with is an image. So it kind of says, well, let's just treat it like an image and treat it like, well, like a human would study an image. A human doesn't like look at everything at once, but a human sort of moves their eyes around and on the image, looks at certain patches, and draws conclusions from that. And this is, on a basic level, this is what a convolutional neural network would do as well. It doesn't just look at everything at once and doesn't sort of get any valuable information out of it, but it looks at different parts sort of sequentially and draws conclusions from that. And that leads us to much better predictions for these kind of images. Okay. Now, that's for images. The big question, of course, is how can we do the same for graph input? And this has been, for a long time, there was no real answer to that. How do you derive a good neural network architecture for this? And very recently, as I said before, these graph neural networks have emerged. So a new kind of architecture for neural networks. And they basically kind of solve that problem of how you work with graphs in machine learning. Now, I won't go into too much detail of how they work internally. That's not important. There's a lot of maths, of course, as you can imagine, but let's just get some intuition. Well, what we essentially want is we want to get outputs for each of these nodes. So we want a neural network architecture that takes the entire graph into as input. We'll see this in the next slide as well. Takes the entire graph and then labels the nodes. If we stay with the behavioral analytics example in a company, we have these employees, and most employees will of course be benign and be not a security threat. So we want the neural network to tell us that, right? We want a neural network that tells us, given some information about the employee, are they just a normal employee, or are they a security threat? So maybe like this person is labeled as a security threat. And then one would have to investigate that further. So this is kind of, this is the idea. We have a label for each of these nodes, right? And kind of the difference from between graphs and normal inputs is, again, that we have these relationships. So in a normal convolutional neural network or neural network that we've seen before, you wouldn't have these connections. Each of these samples would still have like a label. Cats would be labeled cats, dogs would be labeled dogs, but there is no connections between them. In graph neural networks, there is. And that's quite crucial. So what we want as well is our graph neural network to use these connections, because it kind of says, well, maybe if the features of users that communicate a lot together might be fairly similar. So in making a prediction about this user, we can also make use of information about this user. But because this user here, let me choose a different color. Well, because this user here is very far away in the graph from this user, probably we don't need much information from that user. We mostly use information in the neighborhood of this user here. And this is what makes graph neural networks work so well. They can incorporate that information from neighbors as well to make a prediction about a node. So here, when we make a prediction about a single cat, a normal neural network would not consider all of the other samples. It would just consider this sample here. With graph neural networks, we do consider also samples in the neighborhood. Okay, so let's take like a broader view. Here we kind of see the input-output pipeline again. So the input here on the left side is exactly some graph. We've seen that before. We have these features. So this information, these pieces of information that we have about each of the nodes And we have the graph structure. So we have these connections here as well. We feed all of that into our graph neural network. And what we expect as an output is the same graph, but now with these labels assigned to each of those nodes, saying whether that's a security threat or not. Now, internally here, what's happening in one sentence is there's this so-called message passing algorithm, which is the foundation of graph machine learning or graph neural networks. What is happening here is kind of the nodes, the graph neural network sends messages between the nodes kind of in an intuitive sense. And those are, of course, parameterized, and we can tune these parameters, again, as we've seen in the first couple of slides. And yeah, this is basically how graph neural networks work. Now, of course, as you know, machine learning in general is incredibly fast-paced. There's a lot happening. So I wanted to give a broad overview of kind of what is the tool landscape at the moment, and this is actually quite recent. So what kind of tools can we use when we want to perform machine learning on graphs, when we want to use graph neural networks? There is some general deep learning frameworks. So those are here in the top row. And some of those probably sound familiar to you. There's TensorFlow, that's a framework developed by Google, very popular also in production when you want to use machine learning in an actual production setting. And there's PyTorch, that's developed by Facebook. It's kind of the competitor to TensorFlow, is getting more and more popular, especially among researchers. Then there's also MXNet, so it's kind of the Microsoft competitor. And now very recently is JAX. That's not as well known at the moment, but is gaining a lot of traction already among my colleagues as well. So JAX is also developed by Google and used in all of these like famous research labs like DeepMind, which has recently been in the news, all over the news. So JAX essentially is also sort of a very new version of these kind of general deep learning frameworks. And then on top of those frameworks, there's usually graph libraries. So those are libraries which make it easier to perform machine learning on graphs. So they contain sort of the building blocks to build graph neural networks. And there's one that's called PyTorch Geometric, very, very popular. It's built on top of PyTorch, as you can probably guess from the name. Then there's also the Deep Graph library, which is developed by Amazon and also by the creators of MXNet. It's basically a competitor to PyTorch Geometric. Now we also have the Open Graph Benchmark, and this is essentially a tool to compare different graph neural network architectures. There's, of course, there's this sort of general idea of graph neural networks, and then there's multiple flavors. Especially researchers want to compare different models with each other, but it's also good to kind of see what is currently the state-of-the-art graph neural network architecture. So an Open Graph Benchmark sort of makes that possible. And then here we have Giraffe. This is literally just came out a couple of days ago. Essentially, it's built on top of JAX, and it's sort of this new fancy framework for machine learning on graph structure data. Okay, then let's see how graph machine learning, why it has such a profound impact on cybersecurity. The reason is similar to what I've mentioned before. Graphs are so incredibly good at modeling these different scenarios, and that's also true for cybersecurity. So, for example, what you can see here is an actual real-world scenario of a graph of employees in a fairly big company. So you've got all of these nodes; those are the employees, and you have connections between them, which are essentially email communication. And as you can see, a huge graph, and as you can probably guess from this picture, a lot of information and a lot of data that we can draw conclusions from. Okay, so let's see how would that work? What does it mean to do graph machine learning in behavioral analytics? Let's make it a bit more abstract again, like a bit smaller graph. Again, we've seen this before. We've got our users, and we have maybe these documents here, and we want to see, can we, for example, find anomalies in this graph? Because anomalies typically would constitute like a security threat. And we want to use our graph neural network to detect these anomalies in sort of the normal behavior or the normal graph structure. Okay, and there's different yeah, so this is basically here what we can see. This is the goal. We might have someone sort of a security threat here who tries to access valuable data. And of course, we would want to prevent that. Now, there is different scenarios of how graph machine learning can be used in behavioral analytics. So the first one is kind of this cluster anomaly scenario, and there's multiple options. We can start with option A, which is kind of the combined threat. Here. So the combined threat says, well, we look at nodes, and maybe we see that there's something anomalous about these nodes, but by themselves, they don't constitute a security threat. But now we look at a cluster of nodes, meaning a group of nodes or a group of people in this case. So we look at this here, and then we see, well, actually that group now, that does appear to be a security threat. So that those are sort of partners in crime. So right, it's a combined threat that should be taken care of. So this is the first option. Now let me outline the second option, which is kind of more based on cluster baselines. Second option of within this scenario. And yeah, what we think about here is, well, imagine you have two different branches of a company. One is, for example, in Italy and one is in Germany. And then you have a department in that company. Let's say those are those three nodes here. Now you can learn kind of a baseline behavior for that department, let's say in Italy. And now you want to say, well, let's compare that behavior of that cluster, of that group of people, to the same department, but at a different branch in Italy, for example, in Germany, for example. And can we sort of see a difference? And that comparison can, of course, help us in identifying anomalies as well. Okay, so that was scenario A. Now, scenario B is to identify communication anomalies. So here we say, well, this is kind of, this graph represents the normal communication structure. But now suddenly someone kind of communicates with someone who's outside of their normal cluster, right? So if we think about this, like this person's very far away from that other person in the graph. So we would be kind of surprised if they suddenly start communicating a lot. And that is something that, yeah, is somewhat anomalous, and why it would make sense to look into that. So that's the so-called communication anomaly. Essentially, someone kind of behaves, sort of leaves or communicates with someone outside of their usual group. And here, I hope you can see how the graph structure is fundamental to this. You need that graph structure information, otherwise you can't really know what it means to communicate with someone outside of their usual circle. Okay, and then we've got the last scenario, scenario C, that's relative anomalies. So that's when we want to think, it's kind of an extension of that idea of Sherlock, where you define a user-based baseline, right? So behavior or anomalies are relative to a user's behavior in the past. Now we can also define anomaly relative to the behavior of their peers. So we can see, like, maybe this group of people kind of behaves similarly, maybe this group of people and this group here. And so we can see, well, if someone, it's okay if this user here behaves very differently from this user here, because they're not in the same group, not in the same cluster of nodes. But if this person starts behaving very differently from this person here, then this might be something suspicious, right? So this is how we can, again, use the graph structure to define anomalies, not only relative to a person's own past, but also relative to how their peers behave. And yeah, I hope you can see how this is, yeah, an incredibly valuable scenario and a really good tool to detect these kind of anomalies. Okay, yeah, let's draw some conclusions. First of all, I would say, I hope that's clear. Like, graph machine learning is already reshaping a lot of fields out there, because it gives us these state-of-the-art predictions. So there's really many fields where you can't get better results than with graph machine learning. So it's something to have in mind and to really think about. Secondly, something that I want to mention, it hasn't been a topic in this webinar, but that's dynamic graphs. So dynamic graphs, essentially those that also incorporate time information. So where we see, well, how does the network change over time? And this already has a huge impact in other industries. For example, in social media, where we, of course, have a lot of this type of data. I've worked at Twitter before, and of course, here we have we have these dynamic graphs. People make connections every day. There is sort of people like tweets and retweets. So that gives us this sort of dynamically changing graph structure. So that's really important there as well. And this is also based on graph machine learning. So yeah, I hope you enjoyed this episode. We also have an upcoming episode, which will probably be announced soon. And that will delve deeper into sort of applications of graph machine learning for insider threat and fraud management. And yeah, I hope you'll be joining for that as well. Then yeah, already thank you for your attention, and I hope you found this useful sort of strawman's intro to graph machine learning.